A lobster tank in a restaurant is 1.25 meters long by 0.5 meters wide by 90 centimeters deep. Taking the density of water to be 1,000 kilograms per meters cubed, find the water forces on the bottom of the tank, on each of the larger sides of the tank, and on each of the smaller sides of the tank. And since two of our dimensions are in meters, we'll turn the 90 centimeters into meters by doing 90 centimeters divided by 100 equals 0.9 meters. Hydrostatic pressure is given by P equals F over A, or F equals P times A, where P is pressure, F is force, and A is area. Because pressure is force per unit, or P equals F over A, we can compute the total force from a variable pressure by integrating F equals PA. We know that the gravity of the Earth, or the acceleration of gravity, is 9.81 meters per second squared, and the density of water is 997 kilograms per meters cubed. But in this problem, we will round it up to 1,000 kilograms per meters cubed. Here is the surface of the bottom of the lobster tank. Its dimensions are 0.5 meters by 1.25 meters. If we multiply those, we get an area of 5 over 8 meters squared. Now, to find the force of water on this surface, we need to multiply pressure times area. Pressure is equal to the acceleration of gravity times the density of water times the depth of the water. So we know that the acceleration of gravity is 9.8. The density of water is 1,000, and the water depth is 0.9 meters because the height of the tank is 0.9 meters. Multiplying these, it will give us 8,820. And now that we have the pressure, we can multiply pressure by area. So pressure is 8,820 times 5 over 8 is the area, and that will give us 5,512.5 newtons. Now we're going to find the force of water on the large sides of the tank. The dimensions are 1.25 meters by 0.9 meters. And as the tank fills up with water, it's going to start at 0 meters and it will end at 0.9 meters. Since we can't find the depth of the water for the entire side of the tank, since it's always changing, we can use a representative slice of water instead. So here's our slice. And now the slice is always going to have a length of 1.25 meters. And the width of the slice is always changing. We can use delta x to represent this. And the depth of the water is also always changing as the tank fills up, so we can use x sub I to represent the depth of the water. To find the force of just one slice of water, we can use 1,000, which is the density of water, times 9.8, which is the acceleration of gravity, times x sub I, which is the depth of the water, times the area of the slice, which is 1.25 times delta x. And to find the force for the entire side of the tank, we will have to integrate from 0 to 0.9 meters. And it's the same as the slice. So 1,000 times 9.8 equals 9,800. Times x, which is the depth of the water, times the length, which is 1.25, and we are integrating with respect to x. Now we're going to evaluate the integral. So to evaluate the integral, first we can take out the constants, which are 9,800 and 1.25. If we multiply those, we will get 12,250. And then we are left with the integral of x. So to find the integral of x, or the antiderivative, we will divide x by 2 and raise to the power of 2. So we can write that as 1/2 x squared. And then on the integral from 0 to 0.9. And then our final step is going to be 12,250 times 1/2 times 0.9 squared minus 12,250 times 1/2 0 squared. And we can tell that this is just going to be 0. So we just need to multiply 12,250 times 1/2 of the square root of 0.9. And that is going to give us 4,961.25 newtons for the force of water on the large sides of the tank. Now we're going to find the force of water on the small sides of the tank, and it is exactly the same as the large sides of the tank, except the length is different. So, as we did with the large sides of the tank, here's our representative slice. Its width is going to be delta x. The depth of the water is going to be x sub I. And the length of the slice is always going to be 0.5 meters. Now to find Fi, we will multiply 1,000, which is the density of water, times 9.8, which is the acceleration of gravity, times x sub I, which is the depth of the water, times 0.5 delta x, which is the area of the slice. And to find the force along the entire side of the tank, we will have to integrate. We'll integrate from 0 to 0.9 meters, and this will be the density of water times acceleration of gravity times the depth of the water, which is x, times 0.5, which is the length, and we will integrate with respect to x. Now to evaluate the integral, we will do the same thing that we did for the larger sides. Take out the constants, which are 9,800 and 0.5. If we multiply those, we get 4,900. And then we are left with the integral of x, integrating with respect to x on the interval from 0 to 0.9 meters. The antiderivative of x we know is 1/2 x squared. And we already know that if we put 0 in for x, that will just give us 0. So all we have to do is evaluate for 0.9. So we will do 4,900 times 1/2 times 0.9 squared. 1/2 times 0.9 squared gives us 0.405. If we multiply that by 4,900, then we get 1,984.5 newtons, which is the force of water on the small sides of the lobster tank.